Okay, so we are talking about the control rectifier, single phase. Control rectifier. And we have already discussed these things. The converter configuration. Suppose the output current IT is highly inductive load. Highly inductive load. This is T1, this is your T2, and this is your T3, and this is your T4. And this inductance has come from the source. So, if you remember the last class, we have discussed your source voltage, Vs, with the source current Is. So the voltage drop at the inductance is Vs. So if we apply the get pulse here, so here, this get pulse will be given to T1 and T2. This get pulse will be given to T3 and T4. And this is your alpha, this angle should be your pi plus alpha. And if we plot the IS current, I am repeating whatever we have already done. So here, until 0 to alpha, the current should be, if it is IS, then T. So 0 to alpha, I am first drawing the output voltage. Output voltage will be like this, and then it will go like, sorry. If you remember that output voltage will come like this, and then there will not be any voltage during the commutation. There will be commutation here, because during this commutation, this point is your alpha plus E. So this one is that. You have already calculated it, and the output voltage will follow like this. And then there will be another commutation here. Commutation is nothing but the shifting of the current from one set of thyristors to another set of thyristors, right? So this angle, the span of this angle, equal to U. That is your commutation. If so, then 0 to alpha, the thyristor that should be conducting will be T1 and T2. And then alpha U2, pi plus alpha plus this point will be pi plus alpha plus E. Then during this period, T1 and T2 should be conducted. So when T1 and T2 would be, sorry, here T3 and T4, T3 and T4. Okay. So 0 to alpha, 0 to alpha, T3 and T4 should be conducting. That means this one and this one. So current should go like this and should go like this. So then your IS might be equal to minus T3 and T4 conducting. So then the current is constant current, so we should get minus. And during the commutation period, that means your alpha to alpha plus E during the commutation. Can you listen to me? Hello?
Yes, sir.
Yes, sir, we can listen to you.
Okay. During this commutation, so T1, T2, T3, T4, all are conducting. And then your output voltage should be 0. And the current should be shifted from your minus ID to plus ID. It will be N, it goes to here. Can you remember this thing? Hello?
Yes, sir.
This is a question. And this is your IS. And look here, the IS is just passing through the your omega T axis. If it is this point is alpha. Okay? This point is alpha plus Q. Then current is passing through what angle? We have already calculated in the last class. IS is passing the omega T axis. At what angle? Can anyone tell me at what angle? Is it alpha or is it alpha plus U?
Alpha plus U.
Or alpha plus U by 2? Look in this one is U, right?
Oh, yes. Alpha plus U by 2.
Right. So, and also, if we plot the first harmonic or the fundamental component of the IS, if you remember that sinusoidal, this is your IS1, this one is IS1. So, and also look here, and this will what is this? This is your VS. So now VS is crossing at omega T equal to 0, and IS1 is crossing at what point? IS1 is crossing at what point? Omega Tx is crossing at what point? Zero crossing. Zero crossing at what point? IS1?
Alpha plus U by 2. Similar
Right.
like IS.
Right. Yes, and this angle will be known as phi 1, and this phi 1 will be known as displacement angle. We have already discussed it, you have forgot displacement angle, right? And displacement power factor will be your cosine of phi 1. Am I correct or not?
Yes, sir.
And this area we have already found in our last class. AU was omega 2 omega ls ID by pi, right? And then the average value of the output voltage, that was calculated as VD equal to 0.9 Vs cosine of alpha. If there is no ls, then we have lost the area omega ls id. The area will be this one. But if you want to take the voltage we have lost, that will be AU by pi. Right? So that we have to deduct this one. So until this we have covered in the last class. Right?
Yes, sir.
Okay. Now I'm going back to your book. So here, article 6.3.21. So it is mentioned that displacement part factor, as already I have proved that will be cosine of phi 1, that is just cosine of alpha plus u by 2. So it is not exactly going in the middle of the u, that u by 2, but we can always take that thing. Okay. Now, if you equate the input in AC side power with your DC side power, AC side power must be equal to your DC side power with the lossless transmission. If we assume that there is no loss in the conversion, so the input side AC power must be equal to your DC power. So AC power, by definition, we know that this is sinusoidal, the RMS value of your input voltage. We cannot take IS because this is not sinusoidal. Rather than we have to take IS1, the fundamental component. That is your that current only contributes your power, because VS3, VS5 all are 0, so we don't need to consider IS5 or IS3, etc. And then we have to find out the angle between this VS and IS1. This is phi 1. Then we have to write down the cosine of phi 1. That is your power factor. So this is your AC power, and output power. AC power must be equal to output voltage multiplied by the current. That thing that has been described by the equation number 6.28. Is it okay? Hello?
Yes, sir.
So now from here we want to find out IS1. That will be your VD, ID,
Divided by VS cosine.
divided by VS cosine of alpha plus U by 2, because phi 1 equal to alpha plus U by 2, right?
Yes, sir.
Okay. Then with that one, we want to find out the value of IS1. IS1 will be VD, 0.9, GS cosine of alpha, then 2 omega ls ID divided by pi multiplied by, this is your yes, this is your, and then this is your VD. Then we have to multiply it by ID. VD we have written here. So VD we have written here. Then we have to multiply by ID. And then here I'm just doing this one. And then that will be your VS cosine of alpha plus. And that then if you multiply this ID with this one, then this equation will come. You understand it? Hello?
Yes, sir.
Okay, so for the if there is an input inductance Then your IS1, that is the RMS value for the because of the commutation, the IS1, the fundamental value of the current fundamental component will be given by this equation. Okay. Now, just we shall discuss the practical thyristor converter. We are talking about the highly inductive current, but this may not be true for all load. So we want to look at the practical converter. This is the figure of the practical converter. So this part is the same as before. This part. This is your T1, this is your T2, this is your T3, this is your T4. What is this?
Force inductance.
Force inductance. What is VS?
Force voltage.
VS. And the right side part, this part is the load. What type of load it could be?
RL load.
RL load. And although we have taken the resistance very much close to 0, but there could be a resistance also. Okay? So practically, what could be the load?
Practically, it should be inductive load.
Inductive load, yes. And what is this thing then? So this is the this resembles the DC motor. So can you remember the DC motor?
Yes, sir.
There, this is your armature inductance.
Yes, sir.
Armature inductance. This is your armature rear resistance. Although they have taken very much close to 0. And this is, what is this? Back EMF.
Backward EMF.
So this back EMF ED is K phi omega, where K is the back EMF constant, phi is the flux density, and omega is the speed. Okay? If this omega equal to 0, then your back EMF will be 0. At the starting, this back EMF is 0, so this motor draws a lot of starting current, maybe 7 to 10 times than the rated current of the motor. Do you know it? The equation of this one is equal to, say, EA equal to, I'm talking about the steady case. So this is your RD and this is your ED. Inductive, if current is already constant, so then L di by dt, you can always make 0. So then you look here, the current, armature current will be your VA minus ED divided by RD. So at the starting, this speed is 0. So armature current will be very, very high. Have you learned it during the course of your DC motor? Hello?
Sir, couldn't hear your question.
My question was, at the starting of the DC motor, this back EMF is 0.
Yes, sir.
Then it draws a lot of current. That is known as the starting current. Have you studied that thing?
Yes, sir.
Yes, sir.
Okay, can you mute the mic? A lot of sound. Okay, now here, okay, before that, okay, let us study this one first. So the current is, this is your ID current. ID current means that the current through the loop, and this ID current is not now a constant current, rather than it is fluctuating. It is going like this. Can you follow my pen? Hello?
Yes, sir.
Yes, sir.
So this is your ID current, means that this is your load current ID. So this current is fluctuating rather than it is constant. For a highly inductive load, it is a, if you plot it, we have already seen this is your ID, your IDT, only highly inductive load. But for this DC motor, we see that the current is not constant, rather than it is fluctuating with the liquid. So if so, then we want to study, define aspects of this phenomena. Look here very carefully. This, can anyone figure out what is this angle? This angle, which is given already. This is 0. This angle is 0. Then what is this angle? What is this angle? Are you not in the class? Only 26 students are here. What is the reason? Do you have any quiz today?
So there's one quiz during lunchtime.
There is one quiz. Okay, so students are over there, and you are also not very much attentive. Okay. So can it is already written here, and you know that this voltage will be here until your alpha. So this angle is alpha, and then this is your. There will be no voltage after that. If you look at this one, there will be no voltage. So this is your nothing but the, it is already mentioned. This is your commutation period, and after commutation, then again from this one, this T1 and T2 will be conducting, right? And also Vs is higher than your ED. This is your ED. This is your ED. So Vs is higher than ED, so your T1 and T2 must be conducting, and it was fired at alpha, and during this commutation, all the thyristors will be conducting. After the commutation, alpha plus U, then T1 and T2 will be conducting, and then the current will start again up, and then voltage has already fallen to negative, so current must start going to negative, and again here T3 and T4 will be conducting. After this one, then current will start. You understand it or not?
Yes.
Okay. So I'm just testing you. When the current was constant, then we have plotted IS. If it is alpha, if it is alpha plus U, and suppose it is, if it is pi, if it is pi plus alpha, and it is pi plus alpha plus U, then we have already seen that the current was negative, and then current has gone to this IS current I am talking about. Then positive, then it continue like this up to pi plus alpha, then it has fallen down to this, right? So this is your Q. And that we have taken, this is your minus ID, this is your plus ID. But this current is always constant, right? So that this current was constant, that is why we have taken minus ID. Because we have, if you remember that during this commutation period, the current was, U was calculated like omega LS, EIS, and this one the current IS at omega t equal to alpha and is at omega t equal to alpha plus u that we have taken. So we have seen that this one is the minus ID and that one is plus ID. With that one, we got 2 omega ls ID. Can you remember this? And you have already done in your diode case. Yes or no? Hello?
Yes, sir.
Okay. So if you have that output current has the constant, then you from that one you can always plot the IS. Now if this one is not constant, rather than it will have a wave shape like this. So, suppose now the current will have that, instead of constant, the current will have that wave shape like this. Here. And then it has build up. Here. I'm just copying this one. And then the current has come to one value. It has come again. So we don't have the constant, rather than we have a fluctuating wave shape like this. Then we want to replace this IS by this curvy nature of the output current. We want to plot it. Then what will be the wave shape? Here, when your T1 and T2, sorry, T3 and T4 will be conducting here until alpha T3 and T4 will be conducting. That should be the mirror replica of this current. So this current will be your, then I am plotting just a look very carefully. Suppose this is your 10, it should be minus 10. If it is say 8, if it is 8, so then you must go to say minus 8. And suppose this is your 5, then you must go to minus 5. And then from there, have to move, right? This will be your mirror replica. This mirror replica will be like this. And then there will be, during this U alpha to alpha plus U, there should be a commutation like this. And that will be this minimum current. So, okay, suppose this is your ID minimum. So at alpha, then we may take in the middle. Minimum is in the middle. So we may take, this is your minus ID minimum, and this is your plus ID minimum, Then when you want to find your AU, what will be your IS at omega t equal to alpha? Can you see it? Please say something. This should be minus ID minimum, okay? Hello?
Yes, sir.
So write down here minus ID minimum. And here this should be plus ID minimum. And then it will be, after integration, it should be 2 omega ls ID minimum. Then your output voltage will have the expression of 0.9 Vs cosine of alpha minus 2 omega ls, not ID, it is ID minimum divided by pi. That I want to establish. I don't know whether you get it or not because you are not attentive today. So, okay, that is why it is written here, 6.30 equation. Instead of ID, we have written this one, okay, this one. When the current was constant, so this ID minimum was replaced by ID. But since we have like this wave shape like this, so our IS wave shape will be like this. So this is your ID minimum and minus ID minimum, this is your minus ID minimum, this is your plus ID minimum. And with that one, we have found this part as AE and divided by. So from there we got this equation 6.30. And if we go to the output side, here to here we are applying the Kashyap procedure. VD must be equal to LD dID by dt, then RD ID, then ED. Right? It is already a average value. Now we want to find out the average value. We want to integrate it. We want to, okay. Then before integration, we have to multiply both sides by dt. Okay, dt here. So this is ID dt. This is your dt. This is constant. So any constant, if you integrate it, it will remain as constant, right? So this will be over one cycle. This will be average value, and the current at 0, it will be the same. Say K1, it will be also K1. So this part will come at 0. This will be say ID dt 0 and T. This will be capital ID and this is your ID. So output voltage will be your RD multiplied by ID plus. Again, this is natural, right? Because when the current will be fluctuating, although, but average value across the inductance, you know that it will be 0. So the output voltage, the TC voltage will be VD multiplied by equal to RD multiplied by ID. This one. So that has been also established in your book. Yeah. This is the 6.3. This is the Kashyap voltage law. And after that, they have derived the later. Okay. 6.33. Equation number 6.3. So this is your up to this. There are some other topics actually, but okay, we don't have time, as well as we normally don't study in the undergraduate level, but in sometimes we also study. Anyway, you can have a look. So there is example 6.2, and that current has already this IS current. Look here, the current has this wave shape, and this is your ID minimum. This is your plus ID minimum. With that one, there will be no voltage here. Output voltage will be like this. So by using this PSpice, they have found this one. And actually, if I had time, I could have covered this discontinuous current mode of operation. But okay, forget it. Inverter mode of operation actually we should study, but we don't need to study this one. Rather than we switch to three-phase rectifier. Diode rectifier, we are supposed to study the three-phase diode rectifier. Okay?
Yes, sir.
So, to understand these things, let us have a look of a video. That video will help you to understand these things. So, after the video, inshallah, I shall discuss the thing. Let us have a very minutely try to understand the contents of the video. Okay. So this one. Can you see the screen? Can you see the screen?
Yes, sir.
Yes, sir.
Listen.
Today we're talking about a three-phase diode rectifier using just diodes, so the most basic form of a diode rectifier for a three-phase circuit. And when we talk about three-phase, we're talking about three different AC signals, and they are shifted by 120 degrees out of 360. So they're evenly spaced, just like standard three-phase power. So we want to take this AC power and turn it into DC power. So how do we do that? Well, we have this circuit here. These are 6 diodes, and each one, so for each phase, and we have A, B, and C here, they are connected to one diode points out and to the load. Here R is our load, and one comes back around and points to each of the phases. So there's 6 in total, 3 pairs. This illustration works. I like to redraw it as slightly different. This is a different representation, and I just think that this one helps kind of the flow of the current a little bit. Here we have our redrawn circuit on the left here, and then the signals for each of the 3 phases drawn on the right. And this is taken from Wikipedia because it's a very good representation. And here you can see the blue is the A phase, and then B is the red one, and then C is the green one here. So what we're going to do first is look at just this phase. So we're going to narrow in on this area where blue, A is the highest voltage, B is at a middle voltage, and then C is the most negative voltage. When we have V is highest, A is highest here, we have a voltage is going to, current is going to flow through here, and it's going to go up into here. Okay? Because this voltage is the highest among these, so this is the highest voltage, B is slightly in middle, and then C is negative, we know that current, the highest voltage is going to win essentially, and that diode is going to turn on, so D1, and these are going to be blocking because this voltage becomes the highest one, and then this voltage from here to here, so this is for B, B is more negative, so this is actually blocking, so it doesn't go here. The same, we can check the voltage here. If it's the highest voltage, the C voltage is going to be much lower, it's negative, so it's also going to be blocking here. So there's no way that the other diodes can turn on. So only the top one, the highest voltage, turns on, and current flows through here and goes out to this side. Now, where does the current go on the bottom side? Once it gets down to here, the current has to pick a path. So we need to look at the different voltages. So we know that C is a negative voltage, low voltage here, and we know that the B is the middle voltage and A is the highest voltage. So what it's going to do is actually, it wants to go to the lowest voltage. The lowest voltage is going to turn on. So it's going to be our C here, so ABC. It's going to actually go through this one and then come back through our system here. It has to be this one because if any of the other ones were turned on, there would be a violation of KCL or KVL. So, okay, for example, if this one was turned on, that means that, so this is B. If B were turned on, that means that this voltage, it's an ideal diode, so the voltage across it is 0. So this voltage and this voltage must be the same. But this voltage is still higher than this one, so this diode would also turn on. But that violates the voltage law. It can't happen like that. So it goes through to the lowest voltage and then comes back around. If you believe that on this top one, the highest voltage wins, and at the bottom one, the lowest voltage wins, once you've understood that, then it's easy to just go through the rest of them. Here's our next.
So, do you understand what the lady is trying to say? Hello?
Yes, sir.
Do you understand it, or I need to explain it?
Yeah, you can give a small explanations.
Okay. This part she has explained. Okay. Now look here. She is talking about there are three phases of voltage because we are talking about the three phase rectifiers. So here I have already drawn the figure, whether you have seen it or not. Your three phase has the Y connected generator, and this is your N, this is your A, suppose this is your B, this is your C. So now you must know the phase sequence. Are you familiar with the term phase sequence?
Yes, sir.
So the phase sequence is A, B, C. Then your VAN will be your say Vm sine of omega t. VBN must be Vm sine of omega t minus how much?
120 degree.
120 degree. And VCN must be equal to Vm sine of plus 120 degree. Sometimes people say Vm sine of minus 240 degree, right?
Yes,
Sine
sir.
of
Sir, you wrote omega t plus 120 degree.
yes. Vm sine of omega t minus 240 degree. This way we can write down, right? Yes or no? From the power system knowledge.
Yes, sir.
Yes, sir.
Okay, good. So now look here. Here, the first A, phase A has been marked as blue line, right? This blue line is your phase A. And then after 20 degree, the red line, right? Red line is after minus 120 degree. Okay, go back and see. This is your zero crossing, and after 120, that should be zero crossing here. This span must be minus 120 degree, right or wrong? So this
Yes.
is your B phase. Red one is the B phase, and C one, of course, minus 240 or plus 120. So green one is the C phase. Okay. So this is your, okay, I'm changing the color. This is your B, and this one is the C. Now, first we will have to look at which voltage is the highest voltage for this segment. What is the angle of this segment? Can anyone tell me what is the angle of this segment? 30 degree, 5/6. Okay?
Yes, sir.
It will be 5/6. So let us start with this one. So this voltage is the highest voltage. Okay, this is the highest voltage compared to this. The lady told you that this is the middle one, this is the minimum voltage. So here we have already seen that the phase A. So this is your phase A. So of course this diode D1 will be conducting because this is connected to your phase A, and then that will go here. So if it is like this, that this AN voltage already appeared here, right? And this voltage, AN voltage is greater than your PN voltage and greater than your CN voltage, then which diode should be conducting during this phase? Which diode? Tell me. D1, D2, or D1, D3, or D5?
A1.
D1. Okay, then the current will flow like this. The current will flow like this. Okay. The current will flow like this. Now, which path should take the current? You got my point? Which path? So here is that since the return path, of course, the lowest voltage that will be that will we have to take, that will be the return point. Which, so you see that this is the green one. So green one is the which phase C. So green one is the C, means that C is connected to your D2. Am I correct or not? D2 is connected to your C. D6 is connected to your B. Look here, B. And also D4. 4 is connected to your A. Yes or not?
Yes, sir.
So then here during this period, D1 and D2 will be conducting. That she wants to tell you. Okay, let us continue our video.
Top one, the highest voltage wins, and at the bottom one, the lowest voltage wins. Once you've understood that, then it's easy to just go through the rest of them. Here's our next phase. Blue, the A is still the highest, and B is now the lowest voltage. So what we do, we would start through here. We know A is the highest voltage, that's going to win. So the voltage goes through here. This is exactly the same as before. But now when we get down to here, we have to say, where is the lowest voltage? We're going to pick that path to go through. In this case, it's B. So B is here. So diode 6 is now going to turn on, and it's going to go through here. And this one, the other one, is just blocking for the moment. There's no current going through it. Now we move to the next phase, and this time C actually has the highest voltage. A is in the middle range, and then B is the lowest voltage. So we start from the beginning. We know that C is the highest, so actually current is going to flow through here, through diode 5, out of here, to the load, to the other side. We get here, we say, where do we go from here? We'll go to the lowest voltage. We see the lowest voltage is B, so we're going to go through unlettered diode 6 and go back through here. So this is going to be our current flow direction. In this phase, still C is highest, but now we've switched from B being the lowest to A being the lowest, so we're at this area. So again, we start from C, current's going to flow through C, go through to our load, out here. Again, we pick the lowest voltage. In this case, it's A. So A is going to be this guy, so diode number 4. We're going to go through this way and come back around. So there's our path for current. Here we have B as the highest. Now it's switched, so B is the highest, and then A is the lowest. So from B, we go through here, we can go through diode 3, through our load, come back, and go through our lowest one here is A, so we're going to go to A, which is over here. Okay, going through all of these. Here again, B is the highest, but this time C is the lowest, so B is the highest, current's going to go through here, go through D3 again, and then we're going to go through to C being the lowest, 1, 2, A, B, C, which is here. So diode 2, and go through here, and then come out here. So current flow goes this way. So after going through all of the 6 phases, we've seen that the top part, these 3 diodes, essentially make the highest voltage go through, and then these 3 diodes make the most negative voltage be seen at the bottom side. So in this picture, you can see the positive voltage is shown here. What they left out was actually the negative part, which is shown here. So the negative is also followed here. And this is my terrible drawing, I'm sorry. Pretend that it actually follows. And if you do the math on each of these, if you take this portion minus this portion, this minus that, for each of them, you'll actually get at the bottom this nice wave rectifier shown here. So this bumpy part at the top is.
So you understand what she says? No.
Yes, sir.
So this is your say. This is your say. Okay, just a minute. Let me draw it. Okay, suppose this is your, actually, this part is nothing but the negative part of this one. So suppose here, as she mentioned that, if this is your VAN, Suppose this is your VN, and so if this is your VBN, so how we can get VAB? Can vectorically? Is it not
VAN minus VBN.
VBN? So if you do that, so if you this is already negative, then you will get that. If you negate this part and this part, then you write down this part. This is your VAN, say, and this is your VBN. Sorry, negative one. Negative one, your VBN. And if you do that, then negative will go to positive, and finally you will get this one. And that is your line to line voltage. Okay?
Yes, sir.
So now,
is the rectified waveform, and you see that there's 6 little bumps because of the 6 different phases that we went through before. 6 diodes, 3 on top, 3 on the bottom. We can take a 3-phase waveform and turn it into a rectified waveform, which will end up looking like this at the end.
okay. Now, let me share the book of, oh, sorry. Just wait. Where is that course? YouTube course. Yes. Can you see the book now? Hello?
No, sir. It's not visible.
No, sir, not yet.
Very good. Can you see it now?
Yes, sir.
This is from Haruna Rashid, okay? Page number 123. Haruna Rashid. The book we got already. So page number 123. So look here. This is the, what is this? Circuit diagram of?
3-phase bridge.
Right, you are correct. So now how we label the diode? First one is D1, you add 2. So then you will get 3. Then add 2, you will get 5. So 1, 3, 5. Okay? Or in the other way, you write down the odd number of the diode. You got it?
Yes, sir.
Then you add 3. So D1 plus 3, then what it will be?
4.
4. So you got D4. 1 plus 3, then what you will get?
6.
6. And then also 5 plus 3, 8. We don't have, we have to come back, and that will be D2. With 1, 2, 3, 4, 5, 6. Then we don't have. Then 6, you have the 5 plus 3. It should be 8, 7, 8, but we don't have 7, 8. You must come back again, 2. So it will be 2. Okay, you got it?
Yes, sir.
So this is the way you have to remember. Now, we have, as the lady mentioned that we have the A is connected to your first leg. We call it, this is your leg 1, this is your leg 2, this is your leg 3. So this is your, say, A is connected here. So B is connected here and C is connected here. Okay?
Yes, sir.
So what is this? Can you remember what is this? Look here. This is your primary, they say this is your secondary. What does it mean? Suppose you are using a transformer. The primary side is the delta and secondary side is the Y, delta Y transformer. Okay, and this is your generating side, and from that generator we have connected this 3-phase rectifier. Now, Now here, this is the very easy way to understand it. So you follow my pen, okay? So this one, say suppose the red one here, I am putting here. What is this? What is this? We are talking about the three phase, okay? So this is your VAN equal to say VM sine of omega t, VBN equal to say VM sine of omega t minus 120 degree, and VCN equal to VN sine of omega t plus 120 degree, right?
Yes, sir.
And if we draw the phase diagram, so this is your VAN, this is your VBN, this is your minus 120 degree lagging, and from there, that should be your VCN. It should be 240 or plus 120. You can go this way, 2 plus 120. Are you familiar with this concept? Rubel sir has already taught you.
Yes, sir.
Yes, sir.
Now, if you want to find out the AB for this, VAB, you have to find out the B, you have to find out VAB for this. How can you do that? So VAB is nothing but
VA minus BB.
VAN minus VBN, right?
Yes, sir.
So, okay, this is your V minus VBN, say this, that has been here. And then if we vectorically add it, then it should come like this. This is your VAB, right?
Yes, sir.
Suppose this is your reference, then what is this angle? Can you remember what is this angle? 30 degree. So then your VAB will be, this will be root 3 of your VM, right? Can you remember?
Yes, sir.
Yes, sir.
Yeah. Sine of omega t,
Omega t.
plus 30 degree. Right or wrong?
Yes,
Yes, sir.
So this way we can always say, if we know the phase voltage, we can find out the line to line voltage, right? So this line to line voltage has been plotted here. So this will be your say VAB. So VAB, phase sequence will be VAB, BC and CA, okay? So this is, so with the 120 degree apart, you have to draw the BBC. So that has been drawn here by, this is your this is your 120 degree, this is your 120 degree apart, okay? This is your BBC. So let me change the color, maybe the blue one, BBC, this is your BBC, not blue, the green one, right? And VCA, maybe, okay, let us see, this is your VCA, which one is the VCA? So this is your VCA. So this is your, from VAB, this will be, if you look here, go back and it will be minus 240 or something like that, okay? You understand? Hello?
yes, sir.
And then what we do, we also write down the VBA. VBA is nothing but the just negative of your VAB, right? So this will be your VBA, right? And we have to write down also VCA, VAC. And we have to also write down VCA. This way you have to write down. Now start. Here, which voltage is highest? VCB, right?
Yes, sir.
So then VCB, remember C and B. Let us go back and see what is the which are the C and from C. Okay, CB, right? If it is CB, we have already pointed out here CB. C is connected to which diode?
5 and 6.
5. Okay.
5.
And B is connected here where? It
B
is
is
the return path.
to 6.
B is connected to the 6. So 5 and 6 should be conducting during this period. Okay?
Yes,
Okay,
sir.
let us go and see whether it is true or not. Look here, it is 5 and 6. And after that, this one, A and B, we will find the 6th one. And after that, this is the highest voltage. Then it will 1, 2. Then your 2, 3. And this is your 3, 4. and 4, 5. Then you come back 5, 6. So there is a sequence. You understand it or not?
Yes, sir.
Okay, then the line to line voltage, you have to write down this way. This is your line to line voltage. This will be your, this is repeating. This one is coming here. This is your line to line voltage. And this is your line to line voltage. This will come here. Okay? You understand it or not?
Yes, sir.
Okay. Then we want to find out the average value. How can we find out the average value? Suppose this is your zero crossing here, or your origin is shifted here. So what is this span? If it is 0 to pi by 3, and we are taking in the middle, what will be the span? This is span
5 by 6.
pi by 6. And what is the, okay, if any wave, if it is a sinusoid, if it goes like this, so what kind of equation we have to use? If it is a sine wave, what will be the equation? Cosine or sine?
Sine, cosine.
Cosine. So just we have to find out. We have to find out that then root 3 dn cosine of omega t du of omega t. Then you integrate this part. Integrate 0 to pi by 6. Then multiply divided by pi by 6. And your VDC, and you multiply it by 6. That will be your total voltage. You understand it or not?
Can you repeat it once again? The part, why did we take the interval of 0 to pi by 6? I didn't get that.
So, okay, we have to get the average value. How can I get that average value? If you get this area, 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 if you get this area. How many are? How many pulses are there? 1, 2, 3, 4, 5, 6, right?
Yes, sir.
Okay. So here, instead of going all the pulses, let us try to find out one segment. We want to find out this segment, average value, okay? Then multiply it by how many?
6.
6 or 12.
So it will be 12 because we are taking half.
Right. It should be 12. So then you find out the area. So this is the cosine. So you just write down the cosine and integrate it. Suppose this is 0 and this is your pi by 6. So 0 to pi by 6 and divided by pi by 6 and multiplied by 12, and that will give you the total VDC. Am I correct or not?
What if we don't change the origin and take it from 0 to pi by 3? Is it possible and multiplied by?
Yes, 12. You can start from here, no problem. You can start from here, but then you have to find out you see the zero crossing. You have to start with the zero crossing, right? So we don't have the zero crossing. Rather than we can start from here, because that is another. We know that this is the peak value. Peak value is where if you start any way with a peak value, is it not the cosine?
Yes, sir. It's cosine.
So that is why we have taken this way, okay? You understand it or not? We just take this part. So
yes.
So you just take this, you find out the area. You got it or not?
Yes, sir.
Yes, sir.
Otherwise, how you will be able to do it? Okay, now go to the thing here that has been given here. So is it 0 to pi by 6, 30, then 1 by 6. Okay. This is the average value. How it is coming like this? VDC. Oh, okay. Yes, it is okay. So you don't need to multiply it by 12, do you? Do you need to multiply it by 12? Hello?
No,
Yes,
sir.
sir.
No.
Because we want to
multiply the interval by 6.
Right. Okay. So suppose that has been like this, that is like this, and that is like this here. So this is the repeating, right? This is the repeating things. Am I correct or not?
Yes, sir.
So then if we take this one area and divide it by this time period, that will be your average value. Am I correct or not?
Yes, sir.
So these two to cancel, that means 1 by pi by 6, then 0 to pi by 6, then cosine root 3 Vm cosine sine of omega t, that will be your average value. Because this is the repeating. We have done these things in our previous cases. If you remember, if you have a voltage wave like this, and if it is a pi, if it is a 0 to pi, then if we integrate this part and integrate it 0 to pi and divide by 1 by pi, and that is your average value. Can you remember this?
Yes, sir.
So this is the way we have found out. And this average value has come to 1.654 Vm. You understand it? Hello?
Yes, sir.
This is your 3.3. And your RMS value will be this one. You have to square this one, and then you have to take the average, and then you have to take the root. So it is 1.6.554.
The RMS and the average value are pretty close. They are similar.
Sorry?
The RMS and the average value are really close. They are almost similar.
Yes. Do you know why?
No, sir.
Because this is, look here, this is very much close to your average value.
Yes, sir.
Look here, is it not very much close to your average value?
Yes, sir.
Because it is fluctuating in the 6 with a very minor ripple. That is where your RMS value and DC value almost same. That is your ripple factor will be minimum. You understand? Hello?
Yes, sir. Yes, sir.
Okay. So now, okay, what about the current? If we think about the armature current, phase A current. So phase A current, where the phase A is connected, we have to find out, right? Okay, go to the here. Now phase A, look here, this is your A. Here also there is a A. So with this one, only this current and this current will contribute to your phase A. That is why we write down this way. And when it will be returned, then is BA, this one and this one. That means that will be your return path. So that will be your phase A. You understand it or not? You have to find out this is your A, this is your A, and this is your also BA is the negative, A is the negative. So that will be your phase current. Probably you got it. I am going to the figure and you will see it. This will, oh, okay. Sorry, I'm very sorry. Yeah, this is your A. Look here, it is okay. This is your phase A. Because here, A, here also A was there. And what about the direct current? Direct current only, you will get only the, say, D1. Where the 1 is connected, the direct D1 is connected, so they have considered this one. Okay, let us see where it is. Where one diode are conducting. Here one is conducting. Oh, sorry. Here one is conducting. Here one is conducting, and then that this is your diode current, right? And then it will be repeated in the next cycle. So that is why they mentioned that diode current will be like this. This is already here. After that, okay, we have already seen that diode current start from here. We did not consider this current. So that is your this phase. Here the diode D1 will be conducting also. So that is your diode current. So just to have an idea of this one, and you solve this problem. You solve this problem. Which problem? This is your 3.7. This problem is important for your resistive load. You solve it, that may be set in your exam. So in the next class, we shall introduce you the 3-phase control rectifier. All we are considering without LS, okay? When the LS was 0. Because if I take LS is not 0, then life will be very complicated. So inshallah, in the next class, we shall consider the 3-phase rectifier with the control rectifier. That means with the thyristor, and we shall study this one. Okay, and that will be your syllabus of your final exam. So where we have started after the midterm? Well, diode rectifiers, right?
Diode rectifier, yes, sir.
Diode rectifier with LS, without LS, then control rectifier with LS, without LS, then three-phase rectifier without LS and three-phase control rectifier without LS. We have completed up to three-phase diode rectifier without LS. And in the next class, we shall discuss and review the whole things, inshallah, with the control rectifier. So you please tell other students to join.
Okay, sir.
So to take the attendance, 39 students have just recently joined. Not 39, maybe how much? 13 students have recently joined. Let me take the attendance quickly.